Hi friends, welcome back to our series of sessions on energy conservation aspects. Today we shall discuss about transformers. A transformer is a passive component that transfers electrical energy from one electrical circuit to another circuit or multiple circuits. A varying current in any coil of the transformer produces a varying magnetic flux in the transformer's core, which induces a varying electromotive force across any other coils wound around the same core. Electrical energy can be transferred between separate coils without a metallic or a conductive connection between the two circuits. Faraday's law of induction, discovered in 1831, describes the induced voltage effect in any coil due to a changing magnetic flux encircled by the coil. Transformers are used to change AC voltage levels, such as transformers being termed step-up or step-down type, to increase or decrease voltage level, respectively. Transformers can also be used to provide galvanic isolation between circuits, as well as to couple stages of signal processing circuits. An ideal transformer is linear, lossless, and perfectly coupled. Perfect coupling implies infinitely high core, magnetic permeability, and winding inductance, and zero net magnetomotive force. A varying current in the transformer's primary winding creates a varying magnetic flux in the transformer core, which is also encircled by the secondary winding. This varying flux at the secondary voltage or winding induces a varying electromotive force or voltage in the secondary winding. This electromagnetic induction phenomenon is the basis of transformer action, and in accordance with Lenz's law, the secondary current so produced creates a flux equal and opposite to that produced by the primary winding. The windings are wound around a core of infinitely high magnetic permeability, so that all of the magnetic flux passes through both the primary and secondary windings. With a voltage source connected to the primary winding and a load connected to the secondary winding, the transformer currents flow in the indicated directions, and the core electromagnetic or magnetomotive force cancels to zero. According to Faraday's law, since the same magnetic flux passes through both the primary and the secondary windings in an ideal transformer, a voltage is induced in each winding proportional to its number of windings. The transformer winding voltage ratio is equal to the windings turns ratio. An ideal transformer is a reasonable approximation for a typical commercial transformer with voltage ratio and winding turns ratio both being inversely proportional to the corresponding current ratio. The transformer is one of the most widely used electrical equipment in any industry. The main function of the transformer is to either increase voltage or to reduce voltage. The Indian standard IS 2026 Part 1 of 1997 covers transformers in detail. There are few parameters of a transformer which need to be understood. The voltage ratio is the ratio of output voltage to input voltage. This is also called secondary voltage to primary voltage. When voltage is reduced, a current output increases with the same ratio. Alternatively, when voltage is increased, the current output decreases with the same ratio. A typical transformer, we have seen, a transformer requires cooling, which is either by using oil or air. The following types of cooling are generally indicated on transformer nameplates. ON-AN means oil is cooled by natural convection, and air cooling is also cooled by natural convection. ON-AF means oil is cooled by natural convection and air cooling is by forced circulation. OF-AF means both oil and air cooling are by forced circulation. Transformer performance depends on losses it suffers during no-load operation and full load operation. Transformers are classified into two categories: power transformers, which are used in the transmission network for high voltages deployed for step-up or step-down transformer applications like 400 kV, 200 kV, 110 kV, 66 kV, and 33 kV. Next is the distribution transformers, which are used for lower voltage distribution networks as a means to end user connectivity. So distribution transformers range from, which are normally available in substations, 11 kilovolts, 6.6 kV, 3.3 kV, 440 volts, and 230 volts. We see the rating of the transformer calculated based on the connected load and applying the diversity factor on the connected load applicable to the particular industry and arriving at the kVA rating of the transformer. The diversity factor is defined as the ratio of overall maximum demand of the plant to the sum of individual maximum demand of various equipment. The diversity factor varies from industry to industry and depends on various factors such as individual loads, load factor, and future expansion needs of the plant. The diversity factor should always be less than 1. You see the location of the transformer, which is very important as far as distribution losses are concerned. A transformer receives high tension voltage from the grid and steps it down to the required voltage. Transformers should be placed close to the load center, considering other features like optimization needs for centralized control, operational flexibility, etc. This brings down losses in cables. Let us see the losses and efficiency of a transformer. The efficiency varies anywhere between 96 to 99%. The efficiency of transformers not only depends on the design, but also on the effective operating load. Transformer losses consist of two parts, no load loss and load loss. No load loss, also called as core loss, is the power consumed to sustain the magnetic field in the transformer's steel core. Core loss occurs whenever the transformer is energized. Core loss does not vary with load. Core losses are caused by two factors, hysteresis and eddy current losses. Hysteresis loss is that energy lost by reversing the magnetic field in the core as the magnetizing alternating current rises and falls in the reverse direction. Eddy current loss is a result of induced currents circulating in the core. And if you see the load loss, also called as the copper loss, is associated with a full load current flow in the transformer windings. Copper loss is also power lost in the primary and secondary windings of a transformer due to the ohmic resistance of the windings. Copper loss varies with the square of the load current, which is nothing but power is equal to I square R. Then let's see the transformer losses as a percentage of load, which are given below. These are the kilowatt loss on the y-axis and percentage of rated capacity of the transformer. So kilowatt loss will be maximum 2.5 kilowatt for a 100% thing. So these are all the winding losses in kilowatts. This is the core loss in kilowatt. This is how we can see the transformer losses as a percentage of load in the transformer. For a given transformer, the manufacturer can supply values for no load loss, P no load, which is called, and load loss, P load. The transformer loss P total at any load level can then be calculated from P total is equal to P no load plus percentage load by 100 into 2 into P load. Then we have where transformer loading is known, the actual transformer loss at a given load can be computed as no load loss plus kVA load by rated kVA square into full load loss. This is about the transformer losses. Then if you see the control used for voltage fluctuation, the control of voltage in a transformer is important due to frequent changes in the supply voltage level. Whenever the supply voltage is less than the optimal value, there is a change of nuisance tripping of voltage sensitive devices. Voltage regulation in transformers is done by altering the voltage transformation ratio with the help of a tapping. We normally call it as tap changing facility of the transformer available, the off-circuit tap changer and the on-load tap changer. The off-circuit tap changer, it is a device fitted in the transformer used to vary the voltage transformation ratio. Here the voltage levels can be varied only after isolating the primary voltage transformer. The on-load tap changer, OLTC, which is popularly called, in voltage levels can be varied without isolating the connected load to the transformer. To minimize the magnetization losses and to reduce the nuisance of tripping of the plant, the main transformer, that is the transformer that receives the supply from the grid, should be provided with an on-load tap changing facility at the design stage itself. Downstream distribution transformers can be provided with an off-circuit tap changer. The on-load gear can be put on the auto mode or the manual depending on the requirement. The OLTC can be arranged for transformers of size 250 kVA onwards. However, the necessity for an OLTC below 1000 kVA can be considered after calculating the cost economics. Then the parallel operation of transformers is very important when it comes to energy conservation aspects. The design of the power control center PCC and the motor control center MCC of any new plant should have the provision for proper operating 2 or more transformers in parallel. Additional switchgears and bus couplers should also be provided at the design stage. Whenever 2 transformers are operating in parallel, both should be technically identical in all aspects and more importantly, should have the same impedance level. This minimizes the circulating current between the transformers. Where the load is fluctuating in nature, it is preferable to have more than one transformer running in parallel so that the load can be optimized by sharing it between transformers. The transformers can be operated close to the maximum efficiency range by this operation. So that's all about the transformers. Hope you have enjoyed this video.